sharing. Good morning, good afternoon, good evening, wherever you are. MPAI publishes 3 comfort technologies and 5 standards for community comments. And I'm not going to talk about all 8 documents, but on the specific one of connected autonomous vehicle. But let me first give an overview of MPAI. MPAI is moving picture audio and data coding by artificial intelligence. It is an international, unaffiliated, not-for-profit standards developing organization. It develops AI-based data coding standards, but it attaches or strives to attach intellectual property right licensing frameworks that can guide the actual exploitation of the standard. We are a formally established organization, and I mean, what you see may look complicated, but what is important to see here is that we have currently 6 development committees that are in charge to develop standards. And we have also other groups that are working to develop new projects. We are presenting connected autonomous vehicles, but not the final version. I mean, the final version. What we have is very close to final, but in our process, we collect ideas, we define use cases, we derive functional requirements, we develop commercial requirements, then we call for technologies. We get the technologies and we develop the standard. And then, just before the standard is published, we publish the document looking for comments from the community. We try to integrate the comment that we receive, and then we publish the technical specification. What is the main goal of our data coding standards? Is to make explicit, to the extent possible, of course, the computing workflow of an AI application. In this way, a human can select an application whose internal operation they can somehow understand. So we want to give a choice between an AI application that you don't know anything inside and an application that you can somehow understand. We do this by breaking up monolithic AI applications into a set of interacting components that have semantics of the data that is known as far as possible. By this division of an application into components, we allow developers to compete by offering components that are standards, but may have a better performance than an application developed by another. So this is the summary of what I've said. Our standards is component-based, and an AI application is subdivided in smaller components we call AI modules, aggregated in one or more AI workflows, AIW, and executed in a standard environment, AIF. So you understand that a connected autonomous vehicle is potentially a very complex system, and by doing what I am saying, we are providing the means to understand what is happening in a connected autonomous vehicles, and because you are supposed to be transported by such a machine, you are definitely interested in knowing what is happening inside the machine. So all this has been established in a technical specification that is called the AI framework. So this figure gives you a very, very quick idea. We have a specific presentation because we are at the same time with the connected autonomous vehicles. We are also publishing the new version of the AI framework. Before we had, say, the upper part of this figure. You see that we have AI modules, and you see that they are connected. You see that there's a controller, and before we had the controller could access communication API, storage API, access API, MPI Store API. But now, in version 2, we are introducing a security abstraction layer with 6 types of security services. And at the moment, we are activating 3. The other 3 will be left for the future. Second point, any standard creates an ecosystem. In the case of MPAI, we have, of course, MPAI itself developing the standards. Then we have developers developing components, integrators assembling components by the principle that components can be independently developed and then are integrated by a third party. Consumers that use, of course, the entire application. Now, MPAI, because we are dealing with a technology that is particularly critical, we have established an independent non-profit organization called MPAI Store that guarantees that the components are interoperable, trusted, and available. So this is what you see in this standard called Governance of the MPI Ecosystem. So just quick ideas. So we have MPAI developing standards and doing other things that we'll see in a minute. So let's assume that an implementer is taking up one of our standards, develops an implementation. MPAI appoints, but they are independent from MPAI, assessors, performance assessors that assess the performance of implementation. So this implementer submits their implementation, and hopefully the response is that the performance is sufficient. As I said, MPAI has established the MPAI Store, and the MPAI Store has 3 tasks: to verify the security of implementation, to test an implementation for conformance, and to check the performance. Checking the performance means that the MPAI Store does not actually carry out that task, but simply records what a performance assessor, an appointed performance assessor, has communicated. So now, finally, the implementer submits the implementation, the MPAI Store performs its functions, and if everything is okay, then the implementation is made available on the MPAI Store, and the end user can download the implementation, use the implementation, and feedback their experience score. MPAI in these 3 years since its establishment has produced already a significant number of technical specifications. We have context-based audio enhancement, compression and understanding of financial data, multimodal conversation, and neural network watermarking. Then, at the beginning of this year, we have published 2 technical reports on the MPI metaverse model. So, what did we do on the last General Assembly? So we have decided to publish 5 standards for community comment, the process that I have described, with the intention to publish the final version of the standards at the next General Assembly, which is on the 29th of September. Which are they? The first is the AI framework, version 2, that we already talked about. Then multimodal conversation. There's been a presentation yesterday, and this is available on the MPI website. Then we have 3 new standards: avatar representation animation, connected autonomous vehicles, with what we are doing now, and the MPI Metaverse Model version 1 architecture. By the way, also for connected autonomous vehicles, it's not the full-fledged standard, but the architecture. But this is still a very important step towards the final goal. That's not the end, because we have more activities. At the same General Assembly, we have decided to issue 3 calls for technologies. 3 calls for technologies, as I explained before, when we have completed the identification of requirement, functional requirement and commercial requirement, we issue a call for technology. We have at the stage. So we have artificial intelligence for health, object and scene description, and extended reality menus. We also have 3 presentations in the next days. And we have other activities that are still at the exploration level, 2 projects on AI-based video coding, and 1 on predictive multiplayer gaming. Finally, MPI does not live in isolation. Its standards have been adopted by IEEE without modifications. They are the 4th are formally approved, and you see the 33 series. And then we have a 5th one on neural network watermarking that is on its way. And we do intend to convert more of our standards to IEEE standards. And I'm proud to inform that all this has been achieved in less than 3 years. Okay, so that was the general presentation. Now let me go to what is the topic, which is connected autonomous vehicles architecture. So this will be David is not me. David will make a presentation this afternoon at the time that you see here. So connected autonomous vehicles are a great project, and we expect many benefits from this project. And I try to give a few. We hope to be able to replace human errors with machine errors that will not cease to exist, but will have a much lower rate. Humans will have more time to be engaged in more rewarding, intellectually rewarding activities. Optimize the use of vehicles, infrastructure, and traffic management. If we look at from the top of a skyscraper, what is happening in the city, you see, but this is simply crazy. There's no logic in what we are seeing, but connected autonomous vehicles can improve the logic of the system. It certainly can reduce congestion and pollution. It will help people that are disabled or elderly to have a better life. So there are very substantial benefits that we expect from connected autonomous vehicles. So what are we waiting for to make it happen? And so this is the question that I have. So we have 2 options. One is that, wow, this is a very complex thing. We should let the research progress. We should wait for entrepreneurs to make advances in research and manufacturing, and things will happen. This is one way. Standards are not a replacement for industry, for entrepreneurs, for research, certainly not. But it is possible to do more. And this is what MPAI thinks we can do. So what we have done with the connected autonomous vehicles architecture technical specification is to provide a reference model for a connected autonomous vehicle that is broken down into subsystems. We define the functions of each subsystems, and we define the data that are exchanged between subsystems and humans, subsystems and the outside world. But that is not the end of the reference model, because each subsystem is in itself another very complex system, and therefore we want to break down the subsystem in components, and for each component we specify the function of the component, the data that are exchanged between components, the topology of components and connections, and the functional requirements of the data exchanged. So this is the scope of the reference model. This document does not accomplish all these points, but it is a big step forward. So if there is a reference model, what's the benefit? Research can conduct its work, because definitely we need a lot more research in this field. So they can concentrate on one component, keeping all the other components stable, and optimize the operation of the component, keeping all the interfaces of the other components unchanged. Industry can then promote the definition of data format to a status when the research results are mature and when a component is definitely needed in the system. By means of this, user can also know how the machine is working. So this is a pictorial representation of the players. So we have the industry, of course. The industry need to reach users. That's the goal. But they must have products. In order to do that, they invest in research, or they acquire research results, and then we need the standards, definitely, and finally they can put together solutions that users can buy. But we also have regulation that plays an important role, because this affects the safety of humans. So what then are the benefits of a connected autonomous vehicle standards? Is to accelerate the creation of a high-tech market. So we have seen many examples of how a market can be accelerated because of the high-tech components that are needed were standardized. And I like to mention the MPEG story. Digital television happened much faster than it could have happened. Things are different today, but this example stays. And what is the benefit? Because we can have vehicles of higher quality. The prices of the vehicles can be lower. We can enable explainability of the system, and we can assuage the concerns of consumers who may be wary of entrusting themselves to a machine that they don't control, they don't know. It can also do something more, which is to provide the tools for regulation, because standards must include conformance testing. So you know that a certain component must perform up to a certain level. And also performance assessment, in the sense that we can actually measure what is the performance of a particular component. So what is the benefit of a reference model to the market? It's because component manufacturers can develop, optimize the solutions based on the publicly available specifications. And they put their components to the open market. So this in terms of component manufacturing. We're talking about component. Then we have talking here of the manufacturers of the vehicles. They can access an open global market of components that are based on standard functioning interfaces and are tested for conformance using standard procedures. And a third benefit, because regulations are part of the market, can have better knowledge, better interaction, better communication with the market development, and can provide guidance by appropriate regulations. Okay, so that was again an introductory part. Let's now go to what a connected autonomous vehicle is. So a CAV is a system that interacts with a human and understands the utterances set in the mission. So here we have, how can a human interact with this thing? So this is an important component. And actually we have elevated this to the stage of a subsystem. Then it plans the route from here to, say, to a restaurant. It senses and digitally represents the environment. Okay, like we are in the world, and we have ears, and we have eyes, and from them we understand, we create in our mind a representation of the world, and based on that we decide how to move in the world. Then, like humans, but on a different scale, we interact with other humans about the environment where we are. So can do connected autonomous vehicles. They can exchange representations of the world as they have understood it. And then based on that, it can decide how to execute the steps of a route taking the car to destination. And then finally, it implements the decision by issuing commands to actuate the motion decision. So this is our definition of a connected autonomous vehicle. Let me see what is the reference model of connected autonomous vehicle. So here we have a human, and here we have the first subsystem that is called human-car interaction, HCI. The human is saying, take me to the restaurant. So it says, so the human-car interaction understands that and communicate with another subsystem that we call autonomous motion subsystem, AMS, that the guy wants to go to the restaurant. Now, in order to do that, the car must understand where it is, because, I mean, it has to understand. That is a saying, when we wake up, we need to understand where we are. And so it is asked another subsystem that we call the environment sensing subsystem. Let's say the ears and the eyes of the car, and here are the eyes, but also we have identified another subsystem that is called the motion actuation subsystem. Let me say that this is mostly the mechanical part. So because of that, it knows about the position, velocity, and acceleration. Based on that, the environment sensing subsystem is capable of telling the autonomous subsystem where it is, and based on that, the autonomous motion subsystem can provide, say, a route, and if the user approves, the route is executed. How does that happen? Well, as I said before, the autonomous motion subsystem talks to other peers and gets more information about things that the car does not necessarily see. And here you have some examples. And finally, the command to actuate the motion is provided. And here we have also identified the case where a human can talk with other with other entities at the level of the human-car interaction subsystem. And we're happy to hear comments on this system partitioning. A disclaimer is that we are working on the ICT part of the connected autonomous vehicle. You will not find anything mechanical here, if not that we need interfaces with the mechanical part, but they are not part of the reference model. Here we have a set of terms and definition. The first four are related to the names of the subsystem. Then we have environment sensing technology, basic environment representation, and full environment representation. Most of what I'm going to say will deal with that. So what are the elements that the reference model provides for each subsystem? And this is a more elaborated list of elements compared to what I said before. The functions, the reference architecture, the data in and out, the function of the subsystem components, the data in and out of each component, and the topology of the components. And therefore, the connected autonomous vehicles based on this reference model are explainable if the component function and the I/O data semantics are known. And a disclaimer that I make, this is a general disclaimer related to the AIF, the AI framework standard, is that it is perfectly legitimate that two components are merged, but of course the interfaces should be compatible with the rest of the reference model. Okay, so let's go in an analysis of the four subsystems. So the first one, here we have a list of the human-car interaction. It is authentication, of course, conversation with the human for identifying where the human wants to go. Then also general conversation between human and the car. And then another point that we give, I have not talked about the full environment representation, but this is the image of the environment that the car has created. So this can be provided to passengers. I will show this in a minute. And then this is also important, the HCI, we want it to be not an entity that you cannot perceive, you cannot see, but is a speaking avatar that shows a level of, we call it personal status. It represents, say, think of emotion, and you have an idea what we mean. And this personal status, which is inside the car, depends on the content of the conversation. So if it is a sad news, of course, the personal status of the car would be participatory and rather sad. The information that the car is aware of, and also, of course, the personal status of the human, it is holding a conversation. So this is the reference model. So you understand that it's not a simple one, and but let me just be very, very quick in saying that, of course, we have here an audio front end and a visual front end. And from the audio front end, you will see that we have speech recognition, language understanding, and then we have dialogue processing. And these are the usual component of a dialogue system. But we also have an element here, a component in AIM, that is designed to locate and give identifiers to all audio and visual and audiovisual objects that are around the car or inside of the car. Then we also have this component that is designed to provide identifiers of any object that are referred to. Then you will see here the personal status extraction. Personal status is what I was saying. It is essentially emotion, but not only. We also have the cognitive state, a representation of how much I know about what we are talking about and what is my status in that. And another one is the social attitude. So if the passenger is happy, then the social attitude will be one. If the passenger is unhappy, then the social attitude would be another. And then what you see now is that the dialogue processing is using meaning, is using participant ID, because it must know whom the car is talking to, the text, the conversion of speech into understandable text, and the personal status. The speaker ID and the face ID have the obvious meaning of identifying who the person is. And then we have another interesting component here, which is the personal status display. So when the machine has generated a text, it does not just use the text. It uses also the personal status, because it allows to be more complete in its interaction. Okay, so in summary, for all the 4 components, we are using these 5 elements. The standard specifies the functions of the subsystem. And here you have a specification. It specifies the reference model, including the components, all the data. Then a third part is the interaction, is the input and output data of the subsystem with the environment and other subsystems. Then for each component, we identify the functions of the component. And for each component, we identify the data in input and the data in output. So we only identify the data. We do not identify the functionality of the data, and much less we define the technology. I mean, these are important steps that, of course, will be needed in order to have this context of a market where you can post a component and you can buy components. This, of course, is a long-term process, but this standard that we are approving in a month, in less than a month, is the first important step in the total project. Then we have another, which is the environment sensing subsystem. So this it acquires the environment information using all sorts of technologies. It receives the spatial attitude and environment data from the motion actuation subsystem, the part that is more mechanical. Then it produces the descriptors of the scenes as captured from the different sensors. So in the case of humans, the eyes creates a scene, and the audio, the ears, create another scene. But our brain fuses all this into an integrated representation of the world. So this is what we are doing, and it is here. The basic environment representation puts together the different components. We have more than, we have radar, LiDAR, cameras, ultrasound. We also have offline maps. So this is another source of information. We have audio, and of course, we have GPS. Then it creates this basic environment representation and passes the basic environment representation to the autonomous motion subsystem. So here I could spend more time, but I don't want it to tie you up too much. But this is the reference architecture, the second component. This is the list of the I/O data of the subsystem. These are the functions of the subsystems, of the components of the subsystems. And we have the input and output data of the components of the subsystem. Autonomous motion subsystem, it computes the human requested routes. It receives instant by instance a basic environment representation. It communicates with other curves. It produces the full environment representation. Why do we have this distinction? Because the basic environment representation is what the car can do with its own sensors. But the full environment representation is the result of the integration of the information it has received, or maybe requested and received from other cars. And therefore, it has the intelligence to implement the route and sends commands to actuate the route steps by steps. And therefore, also the motion actuation subsystem executes, but it may give a feedback. When you apply the brake, so you see that the brake is not responding the way you want. And so this is valuable information, and the same does the car. So this is the system. So we have the environment representation fusion, which is the most critical thing. It integrates the basic environment representation, but also information coming from other curves. And then we have this other components of a process that, from a decision to go to a certain place, comes into a command that is given to the motion actuation subsystem. We also consider the possibility that these critical data be recorded for whatever reason. Again, we have the input-output data, the functions, and the input-output data of the components. Finally, the motion actuation subsystem. We have it transmits spatial and environmental information from its own system to the environment sensing subsystem. It receives a motion actuation commands. It translates the command into specific commands to its own mechanical subsystem, brakes, wheel direction, and wheel motors. It receives responses for its mechanical subsystem, and it sends responses to the autonomous motion subsystem about the execution of commands. So this is the system. So this is the autonomous motion subsystem that gives command. And this is the part where it sends, it's called the spatial attitude, its position and orientation and the time derivative of it. It is sending to the environment sensing subsystem. So again, we have the input-output data, we have the function, and we have the input-output data of the AINs. I wanted to use 2 minutes to talk about an important integration between the two projects that we have carried out in NP-AI. So we are having another project that is called the MPI Metaverse Model. And by the way, MPI Metaverse Model architecture is another standard that we intended to approve end of this month. So let's first say, what is a metaverse for us? A metaverse is a set of processes that provide some or all this function. It senses data from the outside world. It processes the sense data. It produces entities. It's what we have called the basic environment representation. It processes objects. Of course, there are objects in this environment, and then it decides that to do things in the physical world or in the virtual world that are consistent with the goal set for the M instance, or in our case, to go to a certain destination. To effect that within the capabilities of the M instance, you cannot reach 100 kilometers per hour in 1 second, and complying with the rules that are set for the M instance that includes also the traffic rules. So this is a very quick one page of the Pi-Metaverse model. So we have identified 4 processes: the users, devices, the apps, and the services, and they perform actions on items. And so this is what we have here. We have the human, then we have the device. The device is midway between the universe and the metaverse because it connects the two. And then here we have a user. But what is a user? A user is a process. A user is a representative of the human and acts on behalf of the human. And then it can also become a persona, but it is rendered as a persona. The persona is not the user. The user is a process. And okay, so this is what we have done. So we have a human can be represented by more than one user. And here is what we have done. Here we have 2 cars, and here we have the human-car interaction, and this we have the autonomous motion subsystem. So we assume that these are 2 processes, 2 users that represent this human here. And in fact, the human is having a conversation with the HCI, which is about I want to go here, and so this is the request. These are the options provided, and then the user decides, and then this is going to the AMS that then implements the instructions. But we have also these other aspects where we have this user here in this car A, is talking with the autonomous motion subsystem of car B, and in order to improve its perception of the world. So first of all, this needs authentication, and then an exchange of the representation of the environment. Finally, we can also have this user here talking with another user here. So what happens? So this user wants to see what is seen from the second car, and this can be done. Of course, we need authentication, and then the second car will send the information to the user. So here we have a more detailed list of what actually happens, but I think we can safely skip that. So what is next? We intended to publish, this is published for a request for comment, and anybody is invited to comment on the working draft. Comments will receive the Secretariat by the 26th of this month. You can respond in whatever way you wish, and we plan to publish this architecture document at the next General Assembly on the 29th of September. Next. So this architecture standard is the starting point for the next step, and we need to implement now a standard that gives the functional requirements of the data exchange between subsystem and components. So far, we have identified that there is a need for certain data, but we did not say what this data should do. And the activity will start in October, and that is a good reason for looking forward to working with you on this exciting project and joining MPI with the motto of share the fun, build the future. This is the end of my presentation. Thank you very much for your attention, and I do hope we can have a conversation.